Okay, Assalamualaikum warahmatullahi wabarakatuh, and good morning, students. So let's continue from the previous example, which is part 1. So previously we stopped at this particular point, okay, whereby I did ask you to calculate what is the initial distributions factor for wall 1 at top and bottom, which for these four values I have already calculated for you. So I did ask you to calculate for wall 3, wall 1, wall 2, wall 3 for interchange level A and B for their initial distributions, top and bottoms. So if you have done it, so you're supposed to get the solution like this, which means the initial distribution factor top and bottom for each wall is given like this. So bear in your mind, I just would like to remind that the initial distributions is used for you to distribute the moment, okay, for you to distribute the external moment at top and bottom at the interchange level, in which you distribute this moment, which is 9004 kilonewton meter, which is at, you have calculated it at interchange level A. So you need to distribute what is the moment from 9000 to 4, so meaning that you get these distributions, okay. So you have 0.361, 0.442, so meaning that 0.361 from 9004 will be distributed at the top of the interchange level, and then about 0.442, okay, times with the 9004 kilonewton meter will be distributed just below the interchange level. So basically you have calculate for your distribution factor. So what is the use for this distribution factor? So the use for this distribution factor is to calculate the primary moment, okay, at top and bottoms. So let's now I show you how you can do that, okay. So now you have the primary moment, okay. So the primary moment you get 9004. So at the top above the change level, so now let's fill in this primary moment, okay. So at the moment you can calculate what is your primary moment, and to recall the equations given to you is that primary moment at top for level, so this is level 13, wall 1, the distribution factor as you have calculated earlier, which is 0.361, okay. So meaning that you can calculate here 0.361 times with, okay, 9004. So therefore you get, okay, I will calculate for you, 0.361 times with 9004, so it gives you 3250, okay, 3250. So now your primary moment distribute just above the change level is 3250. And how about the bottom? The bottom is that the factor you have here is 0.442, so therefore you can calculate here 0.442 times with 9004, okay, what did you get? So 0.442 times with 9004, okay, so you get 3979, so almost 3980, okay. So here you get 3980 kilonewton meter, okay. So you now have distribute factor. So the distribution factor at above and below, which is at A plus 1 value, can also be calculated similarly. So similarly, you can calculate similarly for here, which is 6615 times with the top region, the factor is 0.361, so you get 2388 kilonewton meter. And for the bottom part, the factor is 0.442, so 0.442 times with 11760, then you will get 5200, 5200. Okay, so at the moment you have calculate for your primary moment. So the next is we need to calculate what is our secondary moment for the level here. Okay, for the moment that acting at change level A, and also at A plus 1 and A minus 1. Alright, so let's find the secondary moment. Okay, so to recall, this is the symbol for secondary moment. And how to read this? Again, I repeat, moment secondary at tops x about x-axis at for wall J, moment secondary bottom about x-axis at wall J. So the formulation is the distribution factor, okay, times with the mx. Mx is your external moment. So to get here, these are all the parameter that we requires, okay, for you to calculate. So these parameters, which all these parameter has been tabulated in our table earlier. So now is ourself to determine what is the parameters. So if you look here, okay, if I just fold up this a little bit, okay, you can see that delta kxj, which is required for this parameter, is calculated or defined as delta kxj is calculated. This is delta kxj is equivalent to the initial distribution bottom xj minus the initial distribution top. So what does it mean is that for you to get this, meaning that 0.442 minus 0.361, you will get delta kxj. Okay, so let's now we calculate for delta kxj first. Okay, example to calculate delta kxj, let me show you. Okay, 0.442 minus 0.361 is equivalent to 0.081. So you get 0.081 for your delta kxj. Okay, so same goes to the rest. So can you calculate for the rest? Okay, so if you look here, I think you all of you have complete calculate this. So you can see that the delta kxj, which is referred to this parameter, is equivalent to the initial distribution at bottom minus initial distribution at top. So here 0.01 is equivalent to 0.442 minus 0.361. Similarly goes for 0.020, which is 0.108 minus 0.088, and same goes to the others. Okay, so now you have complete this. So but it still not give you what you want, isn't it? Because you are now actually to calculate what is your coefficient factor. So for you to get that, so in this case, in the equation you already have delta kxj. So in this particular case, you need to find what is the coefficient factor here, which is ptxj and also alpha x. So you do requires this value and this value. So now let us first calculate for this value, which is ptxj. And ptxj is the coefficients where it being calculated by distributions of the wall at top divided by top and in summations of top and bottom. So what does it mean is, Okay, as I mentioned earlier, for you to determine the value of this factor, okay, this factor PTSJ is equivalent to the initial second moment of area of the top for the wall J divided by the summations of top and bottoms. So what does it mean? If you look at this particular, I need to fold it down so that it's become more clearer for you. Okay, stop. Okay, like this. Okay, for you to get this value, which is PTSJ, so here is you are now calculating for, okay, there are three separate things need to refer. So you are now calculating for PTXJ for wall 1. Okay, so to calculate the PTXJ for wall 1, so now we are calculate for PTXJ for wall 1. So looks at wall 1. Okay, so where is your wall 1? So wall 1, the initial is 8.3. So you are now calculating for wall 1. Sorry. Okay, so you are now actually calculating for wall 1. Okay, so in this case, so to calculate the PTXJ, okay, for wall 1, okay, PTXJ for wall 1 is equivalent to PTXJ equivalent to negative second moment of area top XJ divided by top XJ plus I bottoms XJ. Okay, so top, so here wall 1. So now let's look at wall 1. So where is your wall 1? So this is your wall 1 top regions, okay, for interchange level 8.53. So you can see for wall 1 is 8.53, the inertia. So you can submit here, substitute negative 8.533 divided by, okay, so top 8.533 plus bottom. So bottoms, okay, bottoms of wall 1. So bottoms of wall 1 is 12.8, okay, which is the mid region. Bottom is 12.8. So here you add with 12.8. So finally, if you calculate this, what did you get? You get 8.533 divided by 8.533 plus 12.8. So you get negative 0.399. So you can round it up to negative 0.4. So that is the way how you calculate for this one. So just now you already calculate this and you get negative 0.400. So the way how you calculate the rest of the coefficient is similar, just like I have shown you earlier. Okay, so if you are talking about bottom, so meaning that for the bottom's factor, you may calculate by using the bottom coefficient, which is here is PBXJ equivalent to IBXJ divided by ITXJ plus IBXJ. Okay, so in here you get the PBXJ, IBXJ. So you can refer, this is for still for wall 1. Okay, so for wall 1, so bottom is 12.8. So here you write it down, 12.8 divided by top, which is 8.533 plus bottom 12.8. So the distribution factor you need to calculate. Okay, let me calculate it for you. 12.8 plus, sorry, divided by 8.533 plus 12.8, then you will get 0.6. So that is 0.6, which you will substitute the value into the bottom ratio, which is here is 0.600. So in this case, I now want you to calculate for the rest of the coefficients, okay, for wall 2, 3, and also at interchange B, wall 1, 2, and 3. So can you calculate now? Okay, so I think you already calculate for the factors top and bottom, which is the one that we need to fulfill in these equations. Okay, in these equations, the one that we need to fulfill. Okay, so as for now, we have calculated this, okay, for top and for bottom, but we still not able to calculate the secondary moment yet, because we need to find what is the coefficient factor here. To fulfill this coefficient factor, we are still required to have this value, which is alpha x. And how can you calculate alpha x? So for you to get this alpha x is given by the summations of the top xj times with delta k xj, meaning that the coefficient factor you need to find, multiply with this, then you will get what is we call as alpha x. So now let's look how to calculate it. So the way to calculate it, okay, so first you need to find what is your alpha x. So usually the alpha x value, you can write it down here, alpha x, and here is alpha x. So this alpha x is encountered for the change level at A, and this alpha x is encountered for change level at B. So alpha x, as said earlier, is the summations, okay, is the summations of wall, okay, the PTXA times with the difference of the distributions. So here you have difference of the distributions. What you need to do is that you need to multiply this, okay, multiply the difference in distribution with the coefficient factor here, and then sum them up. So the way how you're going to do that is like this. Okay, what you can do is alpha x is equivalent to summations and j equals to 1 ptxj delta k xj. So summations means, so now you get the first one is 0.081 times with negative 0.400, okay, plus with 0.020 times with negative 0.400, plus with, okay, negative 0.101 times with negative 0.500. So when you sum all this, you finally will get the solution. So when you calculate all this, you will end up with 0.0096. Okay, so you can round it up so that it will become 0.01. So here the alpha for the interchange level at A is 0.01. So you can record it here, which is 0.01. So for alpha x at interchange level B, similar way you can use as what I have shown here. Okay, and can you calculate now? So if you have calculate, you will get here is 0.030. So finally you almost complete your table. okay, but only the item that you still need to find is the coefficient factor that mainly multiply with the external moment. So for this, okay, so here are the equations. Here are the equations. So with all the parameter that you have recorded in your table, so now you just substitute these equations and finally you will get the solutions. So let me show you the solutions for the first one by using these equations. Okay, so I have now calculate for the value. So if you calculate by using the formula that I have showed earlier, you will get this value. And I will show examples. The first one, how you get negative 0.036. So here is how you get negative 0.036. Okay, so you get all these equations, substitute alpha, okay, 1 minus alpha, and then this is the PTXJ value, which is this value, and then you get 0.081, which is the difference here, 0.081. Alpha x, again you have 0.01 alpha x, and 0.361 is the top value. So if you are calculating for this one is the BTXJ, so the parameter for top at wall 1. Okay, so if you're calculating for wall 2, make sure you are using KBXJ here instead of the KTXJ. So that's how you calculate, and you can apply this. You can calculate similarly for the rest of the value in this box. Okay, so now we can calculate the secondary moment for each wall just above and below each change level X. So in here, in our case, this is the change level X, where the first change level is level A. Okay, we now wanted to calculate what is the secondary moment here and here. So the secondary moment that we wanted to calculate for here and here is calculated by using this formula. So what is the coefficients? So we have calculated the coefficient just now. So if you look at the coefficient, which is negative 0.036, so you can substitute here negative 0.036 times with mx. So what is the mx value in our case? So mx in our case is 9,004 kilonewton meter. Okay, so for the top, so here you get 9,004. So from here, okay, from here you can calculate the value, which is negative 0.036 times with 9,004. You get negative 324.14 kilo Newton meter. So that is for top. So you can put here, whereby you get the value. Oh, sorry, you need to make it negative, and the coefficient's value is negative. Sorry, so negative. Okay, so you get 324 kilonewton meter. So here you get 324 kilonewton meter. So the same way apply to calculate the secondary moment at just below the change level. So for you to get the change below the change level, I will just show you one example here. So instead of using top, you are now MBSXJ equivalent to negative coefficient. So this is bottom, XJ MX. So refer to your parameter table. So bottom is 0.045. So take that value, negative 0.045, times with the mx just below the level change level A is 9004. So then you calculate, so you get 0.045 times with 9004, so you finally get negative 405.18 kilonewton meter. So that is how you get. So here then you fill in the value where you get negative 405 kilonewton meter. Okay, so far we have calculated the secondary moment 324 negative 405 by using these equations. So now to calculate the moment at level above the change level, so you need to do like a carryover, get the distribution factor. In this case you get the distribution factor 0.268, so multiply with 324.14 and you get 0.268 times with 324, you get 86.8, whereby it's almost 87. Okay, 87. So here you get 87, and similarly goes for the bottom. Okay, for bottom, A minus 1, which is M A minus 1 as xj is equivalent to negative 0.268 times with negative 405. Negative 405. So you will get 0.268 times 405. So you get 108 kilonewton meter. So this 108 kilonewton meter, okay, you can fill in this secondary moment column, and finally you can calculate what is the final moment. So the final moment is the summations of the primary moment plus the secondary moment. So you just add them up to 388 minus 87, so you get about 2301. So here 2301, and here when you add up you will get 3579. Here also 3579, and here is 5308. So the key thing is that you need to make sure that at the change level it must be equilibrium, meaning that the upper moment and lower moment, when you sum up at this change level, it must be 0. So finally you get the final moment. So where this moment acting at? Okay, it acting on, so basically this is the what we call it, the answer that I have do it myself in Excel. So this 2300, okay, kilonewton meter is actually acting at this level. So here you will get the final moment acting on level 14. Okay, here is 2300, and here you will get 3579, and here you will get 5308. So that is the final moment. So this is the way how you analyze bending moment acting on the shear wall. So this complete the analysis for moment acting on shear wall. Okay, so similarly you need to apply these whole equations, okay, for the change level at B, where if you still remember, as you can remember, so the one that we solved just now is at change level A, okay, and the level, one level above and one level below. So for change level B, I want you to solve it accordingly as what I have explained, so you can get the change level at top and change level for change level one floor above B and one floor above below B. So you need to come up with this table, okay, but you have to calculate for B top, B bottom instead for A top and A bottom. So this is B plus 1 and this is B minus 1. So good luck. So over the whole answer you can get from this table, which is tabulated in our textbooks. So you can refer to our textbooks as well to check your solution.